So the first lesson is symmetrical components. Okay. So here we will now discuss unsymmetrical faults. First three classes, lesson 19, 20 and 21, we discussed uh, symmetrical faults. Okay. Initially we discussed what are various types of energy system transients, ultra fast, medium fast and slow transients. Then we discussed how to compute the symmetrical short circuit by using Thevenin equivalent. And in the last lesson in 21, what we discussed? We discussed how to do this short circuit computation systematically by using Z-bus method. Now we move towards the next three lessons to compute how to compute fault current for an unsymmetrical fault. Now what is the difference between the approach in case of symmetrical and the unsymmetrical faults? In case of symmetrical faults, the system is balanced. Therefore, we can do the analysis on a single phase basis. Then we can extend that to the three phase system. But in case of unsymmetrical faults, this single phase analysis is not possible, and therefore we need to find out other approaches. And one such approach is computing or using the method of symmetrical components to develop sequence networks. Okay. So first in lesson 22 we will discuss what are symmetrical components. Now just like a balanced system can be converted into a single phase system, any unbalanced system can be converted into three different systems known as positive sequence, negative sequence and zero sequence. Okay. And we do analysis for these sequence networks separately and then connect them. So we see here under completely balanced conditions, the system impedances in each phase are identical and the three phase currents and voltages are completely balanced. They have equal magnitudes in each phase and are displaced in time phase by 120 degree. In a balanced system, analysis can proceed on a single phase basis. Okay. The knowledge of the voltage and current in one phase is sufficient to completely determine the voltages and current in other two phases. However, unbalanced system operation can result in otherwise balanced system due to a unsymmetrical fault. Okay. A system is balanced, but due to a unsymmetrical fault, it becomes unbalanced. The other condition where a system can become unbalanced when the loads are unbalanced. Okay. As in case of a large single phase load. Analysis under unbalanced condition has to be carried out on a three phase basis. Okay. Alternatively, a more convenient method is through the use of symmetrical components. So what you do, either you can go for a single phase analysis, a three phase analysis which is very complicated, or another method is using symmetrical components. So what you do when you use symmetrical components, in this method the three phase voltages and currents are transferred into three sets of balanced voltages and currents. Okay, if you have the notebook, you will mention this, that in symmetrical component method the unbalanced voltages and currents are converted into three sets of balanced voltages and currents. Now we are going to see how these symmetrical components look like. So consider a set of balanced three phase system, which as you know is given by three vectors which are 120 degree apart in phase. Okay, as you can see here, 0, 120, 240. Okay. the set is said to have a phase sequence of ABC. So this is a ABC phase sequence. We can also have ACB phase sequence. Phase sequence matters here because accordingly the positive, negative and zero sequences will be determined. Okay. Now consider an operator alpha. Okay. We consider an operator alpha. So you can mention in your notebook alpha is equal to e to the power j 120 degree. It shows a 120 degree phase difference. It shows a 120 degree phase difference. Okay. So it means the voltage in phase A and voltage in phase B are shifted by alpha square, which is 240 degree or minus 120 degree. So alpha square means 240 degree or minus 120 degree, which is shown here. Okay. Similarly, Vc is equal to simply alpha into Va. It means that it is 120 degree ahead or 240 degree lagging. Okay. Therefore, using this complex notation of alpha is equal to e to the power j 120 degree, the three phase sequence voltages can be given by Va, alpha square Va and alpha Va for a phase sequence of ABC. But if the phase sequence is ACB, then Va is Va, Vb is alpha Va and Vc is alpha square Va. Okay, it is the opposite. Okay, so hope you have written down these equations for positive for ABC phase sequence, what are the various sequence voltages, and for ACB negative sequence, what are the various sequence voltages. Next, coming to what exactly are positive, negative and zero sequence voltages. A set of balanced phasors is, okay, you write down this line, it is very important. So what it says, a set of balanced phasors is fully characterized by its reference phasor and its phase sequence. So if you know the reference phasor and the phase sequence, for example here in this case if you know VA, then you can always find VB and VC by means of this operator alpha. Okay. Now suffix 1 is commonly used to indicate the positive sequence. Okay, suffix 1. So positive sequence voltages are VA1, alpha square VA1 and alpha VA1. And the negative sequence voltages are VA2, alpha VA2 and alpha square VA2, where this suffix 1 indicates the positive sequence and suffix 2 indicates the negative sequence. Now the set of three voltages equal in magnitude and have the same fixed phase sequence is known as zero sequence. So zero sequence voltages are the same. That means VV0 is equal to VA0, VC0 is also equal to VA0. Now you write down this last set of equation 8A, 8B and 8C. A set of three voltages unbalanced, which are unbalanced in general, can be written in this form in terms of phase sequence. VA is VA1 plus VA2 VA0, VB is VB1 plus VB2 plus VB0, VC is VC1 plus VC2 plus VC0. That means any voltage or for that matter any vector can be represented by means of a positive sequence, a negative sequence and a zero sequence. Okay. Now the same concept can also be shown in vector addition. Okay, as you see here, the zero sequence components are in phase. So if you see here, zero sequence components are in phase. Okay, whereas these two represents this one and this one represent ABC and ACB phase sequence, and this shows how a particular voltage VA is addition of VA1 positive sequence, VA2 negative sequence and VA0 zero sequence. Similarly for VB and VC. Okay. Now suppose this VB and VC we want to represent also in terms of the reference phasor, which is VA. So in our case the reference phasors are VA1, VA2 and VA0 plus for positive, negative and zero sequence respectively. Therefore, the voltage VA is, as we have seen earlier, given by the addition of positive, negative and zero sequence. Okay. Whereas earlier we saw VB is given by VB1 plus VB2 plus VB0, and VC is given by VC plus VC1 plus VC2 plus VC0. But those can also be represented by the reference phasor VA1, VA2, okay, in this form. And in matrix form, so all of you are advised to write down this matrix. In matrix form, the sequence network is given by this equation. VA, VB, VC is equal to 1, 1, 1, alpha square alpha 1, alpha alpha square 1, VA1, VA2, VA0. So in terms of the positive, negative and zero sequence component of the reference phasor, we can find out any general voltage VA, VB and VC by using this matrix 1, 1, 1, alpha square alpha 1, alpha alpha square 1. Okay. Using the inverse, we can find out the various sequence voltages VAs by using this inverse from the phase voltages. So, the sequence voltages VA1, A2, A0 can be obtained from VA, VB and VC, okay, the original voltages, by inverting the matrix, which comes out to be 1 alpha alpha square, 1 alpha square alpha, 1 1 1. Equation 10 and equation 11 I suggest you write down in your notebook, okay, because this summarize the sequence symmetrical components, okay. Okay. Now, since we are representing any general voltage vector or current vector by means of symmetrical components, the power that is obtained using the original vectors or original voltages and current must be same as that obtained by the sequence or symmetrical components. So, this proof may be asked in the exam. For a three-phase system with neutral return, the sum of line voltage is 0 and hence zero sequence component is 0 for a three-phase system with neutral return. However, the sum of the phase voltage may not be 0, so that the zero sequence component may exist, and in fact this zero sequence component is many a times used in protection systems to detect an earth fault. Since sum of the current is equal to the current in the neutral, therefore the zero sequence current is equal to 1/3 the neutral current. So, as you see here, the zero sequence current is 1/3 the neutral current. Hence, neutral current is 3 times the zero sequence line current. Now, sometimes a 2-mark questions can be asked that prove that the power that is obtained using symmetrical components is same as those obtained using the original voltage and current vectors. So, this is the proof. Okay, it says that the total complex power is given by the symmetrical components is this, which is same as the power obtained using the original voltages and current VA IS star, VB IV star and VC IC star. Okay. Okay. Now, so this is the only question that is related to this chapter, symmetrical components. So, section 4 in the problem statement, okay. So, you go to question number 1 in section 4.2 in the problem set and solve it, okay. So, with this we complete the lesson 21. In physical class we would have completed this problem in the class,